independent events, one of the things that will sometimes get you confused or you'll mix up, you're going to sometimes mix up mutually exclusive and independent. When we're talking about independent events, we're talking about two events that happen one after another. When we're talking about mutually exclusive, we're talking about two possibilities and whether they can happen at the same time or not. So an independent event is when you have two separate things, but the occurrence of the first one doesn't affect the second one, right? So you're rolling a dice, you're trying to get a 3. The fact that you flip your lucky coin beforehand is going to have no effect on whether you have a better or worse chance of getting the 3 on that dice, even if your lucky coin comes up heads 85 times in a row. And maybe it's only lucky because there's a head on both sides, but I don't know. But you're like, oh, I've never had this happen before 85 times in a row. What are my chances of getting a 3 now? They must be increased. No. And one of the misconceptions out there in probability is this idea. If you have a coin that actually has heads and tails on both sides, and it's 50-50, it's not a coin that's weighted funny in any other way. If you flip that coin and had gotten heads 7 times in a row, people think that next time it must be more likely now to get heads because you've had it 7 times in a row. And some people feel like, oh, tails is got to happen now because it hasn't happened for a long time. So there's a better chance of tails happening because there's been 7 heads in a row. When in reality, this is an independent event. It doesn't matter what's happened before. The probability of that next time is still only going to be 50%. So whenever two things are independent, you can just multiply the probabilities together to figure out the probability of both of them. So in our last example, right, we had probability of heads, which was 1 out of 2, and probability of a number less than 3, which was 2 out of 6. And if we would do 1 out of 2 times 2 out of 6, we would get 2 out of 12. And we could figure that out without having to draw that big tree diagram or that big lattice diagram. So we had the addition rule when we were figuring out the probability of A or B, and the addition rule was looking at a single event, a single thing happening. The product rule is looking at 2 events, or sometimes even more, happening in succession. So the probability of A and B is just equal to the probability of A times the probability of B. So here's a great example. If you had to do the sample space of 52 cards and a 6-sided dice and list them all, oh, you could have the ace of spades and a 1, ace of spades and a 2, ace of spades and a 3, ace of spades and a 4, and have to list them all. It would take your whole page. So now what we're going to do is we're going to say, well, let's use our formula. I know that the probability of the jack of spades is only 1 out of 52. The probability of throwing a 5, 1 out of 6. And so the total probability of both of those happening is 1 out of 312. And we're looking at 2 separate things happening one after another. Because of course you can't sort of, there are 2 things happening. It's not like there's, you pull out a card and you got a 5 on your dice. It doesn't make sense. So, sort of a difference between the addition rule and mutually exclusive and the product rule for independent events. Probability used to be part of the grade 12 curriculum. One of the typical types of questions was bags of marbles. They like to have marbles in bags. But interestingly, there was a whole series of questions with pulling marbles out of urns, which was really like, aren't urns the thing that you put people's remains in? So like, what kind of set of examples, like, oh, I'll just put marbles in this and shake it up and do probability questions. Anyways, we just have marbles in bags. One bag contains 3 red and 2 white, the other 1 red and 4 white. What is the probability that both are red? So our notation, we want to find the probability of red and red. Are these independent or not? Pulling out of one bag, does that affect your chances in the second bag? No. So bag number 1, chance of getting red, 3 out of 5. Bag number 2, chance of getting that red, 1 out of 5. And so total chances of getting both red, 3 out of 25. Part B is a little bit different. The marbles are different colors. Remember in permutations and combinations when you did cases questions? When there was different cases of the same thing? This is an example of that. You can do cases with probability. Why are there cases here? Because I could get a red in bag 1 and a white in bag 2, or they'd be different colors if I got a white in bag 1 and a red in bag 2. So if we look at both of those, so probability of red and white, then we would have to add the probability of white and then red. Red and then white will be 3 out of 5 times 4 out of 5. White and then red will be 2 out of 5 times 1 out of 5. Add those two cases up, and we get 14 out of 25. Same thing in part C. We could do cases. How many cases would there be in part C? Because you want at least one white marble. What's an example that would work? Both white. That would give you at least one white marble. Another example. Red then white. Is that everything? White then red. So there would be 3 cases. So if you wanted to, you could figure out each of those cases. White and white, red and then white, white and then red. Whatever those 3 cases are, you could add them up. So just quickly, white and then white, 8 out of 25. Red and then white, 12 out of 25. White and then red, 2 out of 25. Add those up, and we get 22 out of 25. When you have the word at least, that's also a place where the complement, thinking of the not, whatever is not supposed to happen, might be quicker than counting our cases. So what's the opposite of at least one white? No whites are all reds. So our complement says that if we take everything, 100%, 1, and we subtract the probability of the opposite, which is 2 whites, whoa, red and red, then we should get the same answer. And what is the probability of getting red and then red? It's 3 out of 25. And sure enough, we get exactly the same answer. Okay, I'd like you to try example 3 there. We'll put up the answers in a bit. So in that sample space, event A has been circled in red, and event B has been circled in purple. So what are your chances of getting A and B? Just 1 out of 16. So here, can you see that they're not looking for one event after another? They're looking when do they happen at the same time. Probability of A or B, if we count all the circled ones up, we get 6 out of the 16 numbers have been circled. So are these mutually exclusive? What do we know? If things are mutually exclusive, the probability of A and B should be 0. And since we figured out the probability of A and B is not 0, they are not mutually exclusive. So our justification has to use that idea. The definition of mutually exclusive is that the probability of A and B is equal to 0. And since that is not the case, they're not mutually exclusive. Now, most of the time for independent events, we look at one thing happening first and then something happening after. And that second event isn't affected by that first event. But the definition for an independent event just has to follow that the probability of A and B is equal to the probability of A times the probability of B. So there are cases where only one thing has happened like this, and it still could be independent. And there are cases where only one thing like this happens, and they're not independent. But in order to check, we need to look and see if the probability of A and B is equal to the probability of A times the probability of B. Now, we figured out in A that the probability of A and B was 1/16. And now that we've done our sample space, probability of A, the red circles happened 3 out of 16 times. The purple circles happened 4 out of 16 times. And when we multiply those together and simplify, we get 3 out of 64. Is 3 out of 64 the same fraction as 1 out of 16? It isn't. So then we would say no, they're not independent. So in this case, seeing whether something was independent or not, I would say is not intuitive. You actually had to go to the formula, do some calculations, show that two things weren't equal in order to say no, they're not independent.